start with the fourth lecture. It's a place for me introduced to Luis Núñez Betancourt. He's a research at CIMAD. He's a reference in commutative algebra in Mexico. In this occasion, he will talk about methods in prime characteristics.
Well, thank you, Nico. And thanks everybody for being here. I hope you got enough coffee to get awake. I know some of you, or actually many of you, have a rough travel and night. Okay, so I'm going to start first with some basics of prime characteristics. I'm going to start very slow, but at some point I'm going to go a bit fast. If I'm going too fast, please let me know. Yeah, that would be very helpful for me. No? You think that I'm going either too fast or too slow? Please let me know. Don't be shy about that. What else? Yeah, so I'm going to start with a little bit of basics of prime characteristics. Then I will do some crash course in local cohomology, and then we're going to go back to prime characteristics. I'm going to put some information online. I guess we're going to tell you later how. So for instance, my lecture notes, these ones that I have prepared, it's going to be online at some point, hopefully today, somewhere. Also, the worksheets and then some problems that we're going to have through the week. Okay? You have any comment, questions, something like that, don't be shy to send an email. This is my email. And I love this is working. Okay, so let's start with so for us today, and actually most of the week, phi is a prime number. And E is going to be a natural number. For me, the natural numbers include 0. And usually what I'm going to be thinking is E is going to be an exponent for P. And R is going to be always a Noetherian ring. I'm going to assume reduce. For most of the part, not everything that I'm going to do needs to be, it's especially for reduced rings, but this simplifies life a little bit. And D is always going to be the dimension of R. Okay? So, I said I will start from the basics, so let me just define Frobenius. So, the Frobenius map on R is defined. So we have this from R to R, and this is just the power of P now. Sometimes we're going to take P to the E, so we're going to take the E for Frobenius, and we're just going to compose it actually. Okay, this is a map of rings, and we can do this exactly because we're working in, let me say here, reduced of characteristic P. Okay, and we're going to set the image of this map is word and not that by R P to the E. Okay. Let me just define another object that this is not a window. So now if R is reduced, we take this ring of pivotals. And there are different ways to think about this. The one that I like the most is just think as formal symbols. For every element in R, we have a root. And then I call it this way. And to me, it's a formal symbol where, you know, 1 over P to the E plus R2, 1 over P to the E is what we expect. R1 plus R2, 1 over P to the E. R1 1 over P to the A times R2 1 over P to the A is equal to R1 R2 1 over P to the A. Which makes this arranged, no? Let me erase. Now, I said formally, but I did not define that formally. So let me, a usual question that I have when I introduce this subject is, where does it live? Okay. So if R is a domain, well, we have that R is contained is a fraction field. When we localize at the prime ideal given by 0. And then, because it's a field, we can take its algebraic closure. Then we call this L. So R 1 over P to the A is going to be all the elements inside L, such that this P to the E root, power, is inside R. And this is a well-defined object. But I didn't tell you to assume that R was a domain, no? R is reduced. So R is reduced. One of the first tricks that we learn in a class in commutative algebra is that we take the sum over the minimal primes, these minimal primes of R. So if we take the inclusion that sends an element R to its class in every summand. Well, the intersection is what R is in every single minimal prime, no? But that's just something that's nilpotent, but because we are reduced, that's 0. So this map is injected. But now these are domains. And then we can apply the same trick as here. This is contained in the fraction field out of these domains, and then we take that in the right closure. And then we cut now this L again, and the definition is going to be the same as before. So the same L. Yeah, well, no, it's just like case 1, this is L, case 2, this is L. Or let me cut it. Yeah.
But in both cases, we get the same R, the 1 over P.
Exactly, and it's going to run right over here. So then our P3 is exactly something that numbers are. Well, it's L2 now. And we can do this because this R, by rejection, is contained. We can think as contained here. Okay, so this is going to be our object. So let me introduce a diagram. I'm going to take here. So we have R P to the A. This includes, because it's just the image of a map in R, no? By definition, the image of a red. And then here we have R, and then here we have Frobenius map, which is subjective, no? Because the range is reduced. And then we can see R as contained in R1 over P to the A. Because if something is in R, then when we take a P power, it stays in R. R is a range, it's just with the multiplication. So we have these three flavors. And one thing is that this is just different things, different ways to see the same thing. So this one, if I go from here to here with Frobenius, this is an isomorphism because I'm restricting to the image. And then from here to here, we're going to take the identity, which is our isomorphism. And then from here to here, I'm going to take the identity. And then from here to here, I'm going to call like let me just call like ft del e. So like some sort of Frobenius, no? We take something that's a root. Or to the power, and pretty much by definition, it has to be here. And it's going to be subjective. So because all these maps, or vertical maps are isomorphisms and they commute. We have done, this is just different ways to see the same algebra map. So thinking this as an RP algebra is the same thing as thinking this as, as an algebra over the map, and it's the same thing as thinking this as not. No. But this allows to move, no? A little bit, because here we can think like, I'm not thinking this too, over here. We have R, and then we have contained its pure roots, and then R pure square roots. We can go on in that way, and then we can come back here, square, and so on. So there is people who like to think this as like some sort of dynamical system. I like to think this more like a fractal, because if you are in here, well, this is isomorphic to this. I can take this routine chain and then move it through one of these maps, either to the left or to the right. And these, I like to think this is a fractal of maps. But later we can see, what we may or may not see, but there is a lot of research where you can build actual fractals out of this. What's called p-fractals. So these are so beautiful geometry and even art that you can get from any. We may have a chance to see this. It depends how fast we go in this mini course. Okay. So definition, we say that R is finite if any of these maps is finite. So if this is finite, a finite algebra, if this is a finite R model over this one, so a model over this one, or if this is a finitely generated model over this one. So this is, who knows me, is now people who know me know that this is my favorite. So I'm going to pick this one to the finite. If R 1 over P is a finitely generated R model. And of course here you can put 1 over P to the E, or for every E, or for one E, as long as E is positive, because we have this fractal thing. If from here to here is finite, then this is finite, this is finite, this is finite, and we know that the composition of finite is finite. Yeah?
Are you using both lowercase and capital F for Frobenius, or are they all the same capital?
No, capital F is for Frobenius.
Okay.
And this F finite stands for Frobenius, but sometimes I'm referring to the Frobenius map, not the Frobenius world.
Okay, sorry.
And here, I just like that.
Okay.
Yeah, I'll try to be consistent.
Okay.
And this is a mild condition. So for this convention, we're going to set the convention that R is always, for us, finite. And something that you can see as, let me just mention some examples. A field is finite if and only if, so K is a field, then it is finite if and only if, well, the degree of the extension, 1 over P, this one is finite. For instance, if K is perfect, then it has to be finite. So, if this is the example, let me add an exercise that you may do for fun or in the presentation with Wagner, is if R, if A is a finite ring, then any finally generated A algebra is finite. And also 1, let's say, and 2, localization exhaustion, or completion of the final ring. Completion, I mean like you take a local and then take the magic completion, when M is the maximal inner. Fine. So what I'm trying to say with this is that it's very easy to get the finalities. For those that are more advanced in cognitive algebra, there is a theorem of Kuhn that says that every finite ring is excellent, which we're not going to prove. But I can give the reference later. There is a version of frequency.
How hard it is to find non-finite example?
It's not that very hard. And we're going to do some problems regarding that in the problem session. But I mean, you just take a polynomial ring including many variables, take the fraction field. That is not defined. But there are some ways to play with this a bit more. If you're familiar with Cohen structure theorems, they give a criterion like every complete ring is a homomorphic image of a regular ring. No, that's the strong part of the Cohen structure theorem. You haven't defined a ring, that's absolutely true. It's a quotient of a regular ring, which is very good. But we're not going to see that now. But I'm happy to give the reference later. Okay. So, an extremely important theorem that I think right away gives the importance of Frobenius of this kind of algebra is the following. R is regular if and only if R1 over P2A is a projective R model. So Frobenius does respect singularity of regularity.
Is that for a single E value or all E
For
values?
yeah, again, it's for this one or for P. Let me see. Here E equals 1 for every E positive, or if X is 1 positive. And this kind of thing is gonna show up many times. Not like the same thing with the finite. The game is like you do it for one of these over here, and then you just keep moving. This kind of thing, like that kind of game. Also, I'm not going to prove this, but I want to use this as a start to follow. No? If we were lost in not in the airport, we were lost in the jungle, then we're going to be able to follow the direction. No? This is very, very important here.
This term is regular, right? Not after.
Yeah, regular, yeah. If you got in a finally generated K algebra, and K is perfect, it's the same as smooth. No? So this is like the singularity things you got a geometric person. Okay. And we're going to be playing with this a lot, no? Like, okay, well, what if this is not regular, so this is not free, but maybe if it is very free, not free, but it has a lot of free part, whatever that means, then this is probably, is not regular, but it's close enough. We're going to be playing with these kind of things in the course. And we're going to get nice properties. An exercise, this exercise that I'm writing, they're going to be coming in a problem set for later. So if, if P to the E is equal to the degree of this one. So what I was in case of field, prime characteristic. And R is, let's say, a power series ring over a median. So recursive domain. So let me write this Q to assume that this is a prime. So then the rank as an R module for R1 over P to the E is going to be P to the E plus A times the dimension. Okay. So you can play a little bit like what's going to be the rank of this. And there are different flavors of this if you don't restrict to this kind of things. Okay, so is that the question? We're good so far? Okay. So another definition. So let I, and then now, be an ideal. Then let it Proven's power I is the ideal defined by I, and we're going to note this as bracket P to the E, and this is Fi R. So you take Frobenius, the E iterated Frobenius, this is a D, so we take the image, and then we expand as an R ideal. Other way to see this is an ideal generated by R P to the E for every element in the ideal. And if I is generated by these elements, if I is generated for F1 to F to L, then I bracket P to the E is generated by the peak powers of the generators. This is called the Frobenius power. And this plays a very important role in time characteristic. Let me make a quick observation. So remember that when we have R, we saw that this is isomorphic to R P to the E with F to the E. And what's isomorphic to R1 over P to the E with the map that we call like Frobenius index. So from this, then so under these maps, we have that F E tilde of you take I and then you extend to 1 over P to the E. So this is a map of rings, not isomorphism of rings. So then we take elements in R and then we extend it in the rings of roots. So we do that, when we will take this map, then that is going to give us the Frobenius powers.
Can you say that again, please?
Yes. So if we take the ideal in R, and then we extend in the roots. So then this gives us an ideal in R1 over P to the E. This is an ideal there. We apply this map, then we have to get an ideal here, because it's a ring isomorphism. So what we get is this ideal. So what we're playing is with ideals here, but their extensions correspond to ideals here, the P to the E powers. And sometimes we're going to play with these ones, but we're going to be able to translate certain statements to some things that are totally not. And actually, the first one is about to happen. So, suppose that R is regular. Then we have that by Kuhn's theorem, R1 over P to the E is projected. Therefore, it is faithfully flat, no? It's locally free. So then, when we take the column ideal, so all the elements in R that multiply this into here, and then we extend this in a faithfully flat algebra, then this faithfully flat algebra enters here, no? Because this is flat. So this is R1 over P to the E, in R1 over P to the E, J R1 over P to the E. And then we have this statement of columns, but now of ideals, but these ideals are in the range of P roots. But that's not good enough for me because I like to read that in R, not in the range of P roots. Let's just apply the isomorphism. So now we have a recipe to translate ideals in this range, in the range of roots, to R. So then, this implies that this one we know is I bracket. Sorry. This one translates to taking this bracket P to the E, no? The whole thing. This correlates to the P to the E. So it's I column J bracket P to the E. And this is equal to this corresponds to I bracket P to the E. And then this corresponds to J bracket P to the E. So this taking bracket P to the E commutes with coordinators.
Now we are changing the rings, right?
Follow me?
Now we are changing the rings.
Yes, exactly. We want to go from ring of P roots to the original ring.
Okay, and the column ideals would be taken over.
Here is over R, here is over R, but then you extend, and then he wants to articulate the ring, and here is over there.
Okay, thank you.
Thanks. And then exercise show that these like P to the powers, let me do this, commute with intersections. But wait, let me say find intersection. And the question, does this hold for infinite intersections?
So is exercise for regular?
Yeah, that's right. Yeah, it's going to be a lot of exercises.
But that's for regular?
For regular rings, yeah. Thank you. For regular.
Sorry, President, this equality, the second question ideal is on R1 over.
Now here is R, no, because this area lives in R, this area lives in R. We're working on in R. Here was R over P to the E, but we wanted to translate that something. There was a forward. Okay? So let's see other nice things about these powers. See, sure. Let I contained in R be an idea generated by n elements. Then you will take I n to the P to the E minus 1 plus 1. This is contained in I bracket P to the E. And something that you can see from the definition of this is that this was already contained in I P to the E, no? Because this is, can you see the blue? What?
Yes.
Okay. So this is contained here, no? Because this is generated by some P powers. This is generated by all the P, well, this is generated by all the P powers, and this is generated by all the P to the products. So it has to be contained there. So this proportion is telling us that if we take the sequence of ordinary powers and the sequence of Frobenius powers, these are cofinite, which sometimes sometimes it's important that you are playing with things like multiplicities or certain kind of topologies, stuff like that. This is a nice thing that you can sometimes replace ordinary powers with Frobenius powers. We're going to do some of these games later. Okay. So let's do a proof. And this is surprisingly simple. No? This is going to be, which is like the pigeonhole principle. So let F1 and Fl be specific generators. A set of generators. Right? And then let alpha be an exponent be such that is length, and what I'm assuming by length is the sum of all the entries. So alpha 1 sum dot until alpha sub l. So that this is equal to this exponent. So if we take f to the alpha, which is going to be as we expect, f1 to alpha 1, this is one of the how the generators in I to the L to the P to the minus 1 plus 1 looks like. So this is the generators. So we want to see that these elements belong here. To see that, we need to see that one of these exponents is at this P to the E, no? Because if that happens, then that element to the P to the E is in here, and then it doesn't matter what else we get. It's going to be like that. Is there any question? Are we good? Okay. Okay, so, well, I claim that this happens. So, let's note, if alpha I is smaller than P to the E for every I, then what happens? Well, let's add over all of them, the sum over all the i's of alpha I has to be smaller or equal if we add these L times, no? But L times, sorry, this happens for every I, then it's the same as this is less or equal than P to the E minus 1, no? So we add these, all of them, and this is that adding this L times, so this is smaller or equal than L times P to the E minus 1. Contradiction, because this is equal to this plus 1. Contradiction. So hence, the x is an alpha I bigger or equal than P to the E. And so, f to the alpha is equal to fi to alpha I, so P to the E times f alpha minus, I just going to write epsilon I to refer to the canonical basis that has 1 in I and then 0s everywhere else. Sorry, it is P to the E alpha. Okay? Which, because of this element, is not what this is. Well, we carry that it's a P to the power, so this is inside I bracket P to the. Well. Okay. Let me mention another exercise. That's going to be homework. This is a lot of fun. The far is regular. Then the set of associated primes of R over I is the same as the set of associated primes of R mod I bracket P to the. Okay. So let's suppose for a moment that I is a prime ideal. Okay, so if phi is a prime ideal, this set is only one element, no? The prime ideal. So the telling us is that this element, the set of the primes is going to be also just one, the prime ideal. So it's telling us that I, the the powers of a prime ideal are Q primary. And if we want to think about powers, that when you keep primary things into primary things, the first things that at least come to mind to me are symbolic powers. So, for those part of the family of symbolic powers, let me just give you a quick, really nice application of characteristic P to symbolic powers. So, let me it's funny because I wrote this here, but I don't start over there. I could do here, but you know, it's hard to my start. Okay, so okay, so let me just, for those people familiar with symbolic powers, give some quick introduction. Oh, let me just say, if you're not familiar with symbolic powers and you want to have some fun during the breaks or the weekend or the night or whatever you want to have fun, there is a survey. There is a survey. There is a survey that it was written with Helen Darrow, Alessandro Stefani, Luisa Grifo, Craig Unity, and myself. So you can see there like a quick introduction to symbolic powers and see several aspects of that. Okay, let me define them. So let I contain be a radical idea. So then it's n symbolic power we use define by. So what you do is take this I in the symbolic power. We use this kind of parentheses. So these are the curved ones. And then what we do is we take the ordinary power. Then we localize this at Q. Q is going to be a minimal prime of I. Because I is radical, minimal of associated is the same. So you can put as a prime so you prefer that. And then we take the expansion and then we contract back to R. And we know that, I mean, the original ring may or may not necessarily be contained in the localization always. But I'm going to use notation and just assume this to refer to the preimage of the localization map. And then we're going to, since once we do that, this is an ideal that belongs in R, we can take the intersection. Okay, so this is a algebraic object, I define it with localization, but it has a lot of geometric information. And this is due to this theorem by Zariski Nagata. It says following, let K be a perfect field. And let's take R to be the polynomial ring in the variables over this field.
This,
Yeah.
sorry, that was something, but these Q's contain I, right? These are the
This-
minimal primes containing I.
Well, this is the minimal price of I, but this is like an abyss notation. Most do what I mean. This will be the
Yeah, but I'm confused if it's that contain I or
contain I. One of the primes that contain I, these are the minimal ones with the order given by subset. Okay. So and then take I be a radical idea. Okay. So this is the nice geometric setting, no? We're taking an idea in the polynomial ring, and the case is, you can assume even if you want to go further geometrically, like a right across, no? But perfect is enough. So then, this one is equal to the intersection of all the maximal areas that contain I. So now we're going the opposite direction, all the maximal areas. To the N. So this is over all the maximum in the spectrum of R over I now. Another way to see this, you can also just restrict this more general theorem by Eisenberg and Hoster, when you can just restrict to the smooth ones, the maximal areas that social localization is relevant. So what this is telling us? The elements here are those areas, those elements here are those polynomials, which we can think as functions, or as polynomial functions, that for every close point in the variety defined by I have ordered at least n. So Jack and other people like to think this as a higher version of Hilbert-Knudsen instance now. Because
If the symbolic powers are not defined only for prime characteristics,
no,
it's
here.
more general.
Yeah, well, yeah, it's one of the things that I'm just, because I want to have the same, be consistent with the notation throughout the course. I said prime characteristic, but this is defined for any ring, even mixed characteristic or, yeah, or like the integrals, and you make up like really nice theorems over there too. For instance, this, but let me just mention theorem, and then I'm going to give some comments about this. So this has a lot of geometric information, no? Because we're looking at the polynomial functions that have order at this certain point. So this is geometric. Well, I like to think this is a geometric interpretation of symbolic powers, but they also have a differential interpretation. This is the same as other polynomials, such that when you apply a differential operator, it stays in I, as long as the differential operator has order at most n minus 1. I know I have not defined differential operators, but by the end of these 2 weeks, you're going to know more about differential operators, because there is a short course by Claudia Polini in which she is going to talk about derivations of differential operators in community value. For the moment, if you don't know what this thing means, in what characteristic 0, just take partial derivatives, partial derivative with respect to this I to the alpha 1, then blah blah blah, partial derivative with respect to x to the d, alpha d, such that these alphas have length at most n minus 1. Okay, so in particular, the second symbolic power are those polynomials such that when you apply the derivatives, you stay in I, and also there are union in I, not that. Yeah, Christian?
How does this construction compare with jet bundles over the platform?
I don't know. But let me think about that, and I may be able to answer tomorrow, or may not. But we'll try.
What's the subscript on the differential on D?
R over K. So it's just like trying to denote like the differential operators over R that are K linear. So like the partial derivatives or products of partial derivatives. But there are more. There are other kinds of. And if you look at the survey, there is something called differential powers that relate to symbolic powers, and there's a whole theory over that. Okay, so these elements have algebraic nature, geometric nature, differential nature. So they are very versatile. And they play an important role in commutative algebra. They have appeared in several theorems. My favorite application is the Hershon-Lichtenbaum-Banschen theorem of local cohomology, that we may or may not discuss at some point. Probably not, to be honest. But I will try. Okay. But yeah, more on this next week. Okay? So first, let me mention some comments. but not always equal. I'm going to give you a quick, simple example. So if I is generated by x times y times c, x, y, c, in a polynomial ring, any polynomial ring, in 3 variables, you can see that x, y, c is inside the second symbolic power, just by applying derivatives, as we know. For that, derivative with respect to y, so with respect to x is yc, and it's going to be in I. And then people do the others, it's going to be the same. But it's not in the second ordinary power, no, because this is generated in degree 4, because you just take products of this. So symbolic powers are usually not equal. Okay. And second fact that makes this even stronger. I may get disappointed, but it's not disappointing. It's actually very reassuring. You take the symbolic Riesz algebra, which is constructed very similar to the Riesz algebra. So you take the ring, contain it in R. We're going to take a subring of R with an extra variable t. And we're going to look at degree t, at every degree n, we're going to take this. This is going to be a greater ring because this is a greater ring, where the gradient is given only in t, because I symbolic A times I symbolic B is contained but not necessarily equal to I symbolic A plus B. And this is something that you can prove from pretty good exercise that I'm just going to add. Okay. This symbolic Riesz algebra, unlike the ordinary Riesz algebra, because this is not exactly true, we're going to have that this may be non-notarial. It's possible that this is non-notarial. Could fail to be notarial. So, a lot of things that are done for ordinary powers, like the stabilization of debt, and a lot of things that are done, in part use that this Riesz algebra and other algebras associated to this one are notarial. Like some of these theorems about limits of Castelnuovo rule for regularity. A lot of things are known for ordinary powers, are thanks to the Riesz algebra being notarial. But those kind of techniques don't usually work in this setting. Okay, and let me mention another property. Which connects to this. The associated primes of R symbolic, any symbolic power is equal to the associated primes of our R, which is what I promised, the connection with Frobenius power. In particular, if I is a prime Q, then the symbolic power is also Q primary element. So let me mention something to me it's a fact, but I'm not going to give a proof because this is a meta fact. It is very hard, well, at least to me, to know when symbolic powers are equal to ordinary powers. Very hard. Pick a random idea. Pick a random square-free monomial idea. And then tell me if it is, if the powers are the same. It's not that easy. Even in the monomial case that may look easier, it is not. In fact, there is a, I think, $20,000 prize for a conjecture. So there is a conjecture. equality force for free monomial ideals. And that's called the packing problem. But you know, I think it's not, it was $20,000, but I think there was a time limit that I think that passed. So maybe it's just you will do it for free. But we will move on.
Maybe if we do it, you will give us a prize.
I don't think so, but probably you will get a very nice paper that probably will give you like some other prizes and a tenure in some good institution. Yeah, I invite you. Yeah, I'm following this card, no? Like there is something the Ten Martini theorem. This is the bottom Mescal conjecture. But the vacuum problem. Okay.
What is the conjecture?
Oh, please allow me not to say it because then I will take a lot of time to define it. But it is in the survey that I mentioned. And also, I just mentioned Elisa Griffo has some lecture notes on symbolic power because she just gave a full course in this topic. So she did a lot of these things very deeply. And you can find them on her website. So what I'm going to give you as an exercise is if I is a radical completing the section, so it's just a radical idea generated by a regular sequence, then this equality is true. At the end.
Is complete intersection?
Yeah, yes, I is complete intersection. Also, Jonathan and myself have an algorithm to see how to verify this for monomial ideas, which actually is characteristic free, but it's inspiring for values. So we're going to talk about how you can do combinatories for values later in this course. So there is a lot of things that you can do using Frobenius to solve problems in combinatories, but that those problems are characteristic free. We don't have to use this powerful tool that Costa and Kennedy have used a lot to obtain, mod P, like relation to mod P. You can skip that when you focus in combinatories. But we're going to talk about more about that later. Okay, so there is a technique to check when this happens. But it doesn't have to check, but opens different kinds of ideas or kinds of lines of attack. So this is theorem by Trinity, and Vasconcelos. That says the following. The theorem is more general, but I just want to go to the case that I'm most interested. Suppose that we're in a polynomial ring. And again, I is a radical idea. Then, the symbolic powers are equal to the ordinary powers for every n, if and only if the associated gradient of R, which is take the sum of I over n, I to the n over n plus 1. This is the usual associated gradient. You are familiar with the Riesz algebra, which probably you are just, the Riesz algebra, just take the S here and take that's the Riesz algebra. So you do that, then this is the same as the Riesz algebra over the expansion of the I in the Riesz algebra. So the theorem is this happens if and only if this ring is reduced. Again, this theorem is more general, but for purposes. Okay, So it's very hard to know what the symbolic power is equal to the ordinary power. Okay? But then the next question, but we know that the ordinary power is always contained in the symbolic power. So the other question is, when the other thing happens? When the symbolic power is contained in the ordinary power. That's, or well, if we have that, then it's the quantity, no? But maybe not the symbolic power, the exact n symbolic power, maybe some linear version of that. And this was proven by Irene Swanson. So if we take, again, this is more general, but I want to focus only on one thing. This actually works for every local, complete local domain, but you can prove it as here. The radical like that. Then there exists a C in N that depends on the area, or it's a C, but take it as CFI, such that the Cn symbolic power is contained in the ordinary power for every n inside. And as we already know, the ordinary power is contained in the symbolic power. So again, we have that these two sequences of powers are cofinite. So they give the same topology. You can do some games with that, with open homology, and so on. But that I, well, in her theory, depends on the T depends on the area. And okay, I'm going to give you an example. Like, we would like to compute this here. Example. You remember that application of the 3 and 4? Yeah?
So now that you mentioned that they give you the same topology, the formal symbolic powers and those regular powers, can you define formal schemes using symbolic powers?
Yeah, I think so. But I need to think a little bit more. But I think so.
Thank you.
The natural numbers in this case include the zero.
Yeah, always. For me, always include 0. Yeah, but if it's 0, then this is just R and R, no?
Yes.
Okay, so let me do an exercise. So now suppose that R is regular. Let Q contained in R be a prime ideal of height H. Then there's a Q symbolic H p to the e minus 1 plus 1 is contained in Q bracket p to the e. This should look familiar, no? That application that we have of the Pigeonhole principle. But in the Pigeonhole principle, we didn't have an H, we have the number of generators. How we prove this? Well, let's just do localize a Q. If we localize a Q, we know that Q is generated by H elements because our localized Q is regular of dimension H. And this is going to be the maximum right there. That's how we obtain that. And this is contained in P to the E. Okay? So it would be very tempting. What is it would be very tempting to write the following conjecture, which was stated. Can you see the red fine? Okay. By Harborn. There was Q, symbolic H, replace the P to the E for N, as we have n minus 1 plus 1 is contained in q to the n for every n. That would be tempting, no? Because it happens for p to the a, it may happen here. I'm gonna give you a spoiler for next time. This is not always true. I'm gonna mention some examples, but I'm not gonna prove them. But I'm also gonna give a solution or a fix to this, and that's gonna be proven. But this is gonna be next time or Wednesday. It depends how fast we go. Okay. But it can make sense, no? Sometimes you can do this for some P, you can do it for n. Sometimes you can play this kind of games. Something that I want to mention too here. This is also true. This exponent in the symbolic power is smaller or equal than h to the p to the a times p to the a. So this is contained here. This is contained here. The term is contained this one. Okay. This is going to play an important role in a moment. Okay, so we're ready to prove, to give a nice application for prime characteristic to symbolic powers. So notice that, sorry, I say, so, yeah.
This theorem, this function,
Uh-huh.
is true if you take a regular ring or other ring.
No, it works for a complete local domain.
Okay.
Yeah, I just wanted to keep things as simple as possible. But yeah. But in that case, depends on C. And there is a conjecture that C is uniform. But you can see here, if carbon conjecture were true, which we know is not, then because of this one, if this were true, then we could take H, that C would be the height of the prime ideal, no? And the height is always smaller or equal to the dimension. So then we will have that, we can take C equal to the dimension uniformly. Unfortunately, this is not true. But the consequence it is, and that's the theorem that I want to mention. This is a theorem by Hofstede and Künneke.
Luis, there is a question.
On the last word, is the E any E? Or
Yeah, for every okay, so theorem by Hofstede and Künneke. So let R indicate the regular vector ring, which I'm going to write as R there. And Q contains that be a prime layer of height H, then Q symbolic Hn is contained in Qn for every n. And as a consequence, we can pick a uniform bound. Where D, remember this is the dimension of the ring. There is a version of this for any radical ideal, which you are going to do in the problem session. Okay, so let's prove this. I want to mention, we're going to give the characteristic P proof, which is due to Hofstede and Künneke, but before that there was a characteristic zero proof using multiplied ideals by I, Lasserfeld and Smith. And then there is a mixed characteristic version by Ma and Shui. Oh yeah, and I forgot to mention, there is a version of Zariski-Nagata for a mixed characteristic, also by Stephanie, Griffo, and Jeffers. Okay. Okay, let's prove this. I'm going to prove this in less than 15 minutes. It's really good. And I will show the power of Frobenius. Okay, so first case, if Q is the maximum ideal, we're done. Because the maximal ideal in a regular ring is denoted by a regular sequence, no? So it's a complete intersection. So then the molecular is the height n, this is the same as n, no? Symbolic powers and ordinary powers are the same. Then this is contained in m to n. I guess, yeah. Even if h is equal, I guess h is different than 0 now. Because otherwise let me assume that it's not that 0. But this is true even if 0 now. So, well, let me, if q is equal to 0, done. Okay, what's in q different than 0? Okay, now if the dimension of the ring is equal to 1, done. Because it's local, then there are only two options for a prime ideal, being the maximal or being 0, which is the previous case. So now we are going to assume that the dimension is at least 2, that the prime is not maximal, and the prime is not 0. Okay, we're going to focus that. Okay, so there, no, we fix an element in Q, H, N. Okay? We're going to prove that this element is in the ordinary power. So, and now let's fix an E inside. For the moment, this is going to be temporary. This is a permanent fix, this is a temporary fix. That's why we went together in the same sentence. Different kind of. Okay, so then by the division algorithm, there exists A and B inside N, such that P to the E is equal to A times N plus B, with B in between 0 and N. Okay? So we fix the R. In order to fix the R, we have to fix the N, no? Okay? And then after this is fixed, you give me any E, and I will fix it for a little bit, and then I can do apply division algorithm by N to P to the E. Okay. So thus R to the A, this is inside Q to the symbolic H N to the A. And then I mentioned that symbolic powers behave well, they make a graded family or a filtration. So this is going to be contained in Q, H, and A. It's not the same, we don't know that, but it's contained. Now, okay, so thus we will take RA and we multiply by QHN. This is contained in RA, Q, symbolic, QHR. Why? Because HB. Because B is strictly smaller than N, no? So, and then we know that this element was in Q, symbolic HAN, and this has to be in symbolic Q, HB. Symbolic contains ordinary. And then this behaves well. So this is contained in Q, H, A, N plus HB. Let me just rewrite this as H times AN plus B, which we know is B to A. From what we applied the division algorithm, symbolic H, B to A. And then we look at the homework in the future. This is contained in Q bracket P to A. Okay, so what we have? So we have that this one is contained here. So if you give me, let's just forget about this thing in the middle, and then take the power to the n. Everything to this to the power to the n, and this to the power to the n, and then the containment stays. So those r to the a to the n, q to the h n squared, so which is the same of pressing this to the n, is contained in q bracket p to the a to the n. Exercise, symbolic power and ordinary powers commute. So this is the same as q to the n to the bracket p to the a. This is very easy to see that this commute just by taking which out the generators. That's not problematic. Okay? So now, let's fix an element C inside q to the hn squared minus 0. We can do this because q is not 0 now. Okay? And notice that to do all this exercise, we have to go through P to the E. But right now that I'm choosing C, P to the E is not playing any role here. So what happens? Well, you multiply C times R, then C R P to the E is equal to C R A N times R B. And because this product, so we know that this times this one, in particular this times C, is going to be contained here. We know that this times this one, which is a multiple of C R A to the N, this has to be in Q N bracket P to the E. Okay? Are we good so far? Okay. So now, what is telling us? This is telling us that C is inside the column layer of Q N bracket P to the E R P to the E. You are familiar with column layers, this is the same as taking this one. And because its principal is the same as taking this. And we know that taking Frobenius powers commutes with column layers, no? So this is the same as Q to the N plus R bracket P to the E. Okay? So what happens if R is not here? So if R is here, but R is outside Q to the N. If R is outside Q to the N, then Q to the N times R can have 1. One cannot be an element here, so this is contained in the maximal area because we're in the rotor ring. Then Q to the N, R to the N, this bracket P to the A is going to be contained in M bracket P to the A, which is contained in M P to the A. But we have that C wasn't here. C isn't here. And C does not depend on E. So let's forget about our temporal assumption on E. So we have that, and we can do that because how we choose C does not depend on E. So we have that C is inside the intersection of R E of Q to the N R bracket P to the E, and this is contained in the intersection of R E of M P to the E. So by Coulomb intersection theorem, this is equal to 0. So E is equal to 0, contradiction. Huh? So this has to be the whole thing, and means that R has to be in O1. Yeah, this theorem is around 2006, I think. 2006 or 2002. Okay, thank you. So it's 20 years ago now, but Frobenius has been around. Symbolic for long further. Symbolic powers have been for a long time, and this is just like a clever, not very technical application of a very important theorem. So we have probably 3 more minutes. I think I'm not going to do any local homology today. We do it tomorrow. But I hope this first lecture tells you that prime characteristics can be helpful for the things that have to do relate to things that are the prime characteristics. And in fact, we use this technique of reduction to characteristics speed. You can also recover some first-class characteristics here using this. Okay? Well, that's it for today, and see you tomorrow, and today in the problem session.
Any questions or comments?
I have a question about the conjecture, about the characterization of the unit for which of the square free monomerias for which the normal form and the symbolic form is the same. Is there any result for HPLs?
For HPLs, yeah, actually for HPLs is a theorem of, let me just remember, I don't want to miss the name. It is Gittler, Valencia, and Villarreal. Okay? Or Gittler, Reyes, Villarreal. Yeah. Is that for binomial shaders, then you have the quality if only the graph is bipartite. So you have any odd cycle. And I think is the marginal case where the conjecture is solved.
So the version of Coulomb's theorem you stated, why is that the same as Frobenius being flat?
Because I'm assuming finite.
Okay.
Yeah, faithfully flat, but flat for finite generated model is the same as Frobenius. Oh, yeah, you may get lost when we're going to lunch and you can follow one of the organizers or the local people to get the lunch.
So I also guess the problem session is at 4, I guess?
Yes.
And it will be here, I guess. Okay? So the other days we're gonna split and we're gonna use 2 rooms. Today there's gonna be only 1 problem session.